Hi, my name is Anis and this is
Libya, and we both are responsible for data analysis and computations in
Hi,
Excel.
my name is Nurul Natasha Shazwana and I work together with Myra Ajira on focusing to justify the project's relevance and interpret the results, which we articulated the purpose of the project, outlining the significance of studying capillary pressure and relative permeability. We also analyze the data, providing insights and interpretations that help shape the conclusions of the project.
Assalamualaikum warahmatullahi wabarakatuh and good afternoon. My name is Nur Myra Ajira binti Manso, student ID 22005570. So my role in this project is I justify the project relevance together with my friend Natasha Shazwana, and also we interpret the result. Other than that, I also articulate the purpose of this project, outlining the significance of studying capillary pressure and relative permeability. And also, I analyze the data from the scale report, from the Excel, and then we interpret the data so that we can come up with a conclusion.
Hi, my name is Nur Ibrina Natasha binti Idris. My student ID is 220077 and 11, and my part in this assignment is basically I handle the video editing, including designing and doing the slides presentation that will be shown in this video later. I think that's about it, and I think we can get to start with the video. Bye.
What is capillary pressure? So capillary pressure is the pressure difference across the interface of two immiscible fluids, which can also be said as the difference between the pressure of non-wetting phase and the wetting phase across the interface of two immiscible fluids. And we can use the formula PC is equals to P and W minus PW to find the PC. So, how can we calculate capillary pressure? So, there are three methods to calculate capillary pressure, which are porous plate, mercury injection capillary pressure MICP, and also centrifuge. What is porous plate? So basically, porous plate is a semi-permeable membrane or a ceramic plate with controlled pore size is used to desaturate samples and determine capillary pressure and water saturation in rocks. And what is mercury injection capillary pressure MICP? This is a commonly used technique for measurements of porosity, pore throat size distribution, and injection pressure versus mercury saturation for many types of rock. Now, let's talk about centrifuge. So, what is centrifuge in general? So basically, it is a mechanical technique in which centrifugal force is used to separate components of mixtures based on their density or size. So, it is also a method that can measure both the drainage and imbibition capillary pressure curve.
Relative permeability is a ratio of effective permeability to a reference permeability. Relative permeability (KR) is the ratio of the permeability of a porous medium to a particular fluid in the presence of other fluids to the permeability of the same medium to that fluid alone. It is given by K effective divided by K reference.
The measurement of relative permeability, it has two types of method. The first one is steady state method, where the relative permeability of each fluid is calculated in equilibrium condition, where the flow rates and pressures are stable at constant condition. And the second one is unsteady state method, where the relative permeability is measured by observing change at flow rates or pressure over time at varying conditions.
Before we start to interpret the permeability curve from the capillary pressure curve using Purcell, Brooks-Corey, and Corey method, we plotted a graph of capillary pressure PC bar versus water saturation SW obtained from the scale report. This tabulated data and graph is needed as it is part of the method's calculation and also the data representation. So, our chosen rock sample is sample number 404.1 with the depth provided is 3,596.17 meter, and the rock sample that we use is the chalky limestone rock.
For the final model, which is percent model, value of gradient negative 1.524 and lambda obtained is 0.656 is used to find the relative permeability of air and water using the equation shown. The shape of percent relative permeability curve is different from the Brooks-Corey. The curve is symmetrical. The same case in Brooks-Corey model also applied in this curve due to the adjusted irreducible water saturation. The green curve represents relative permeability of air, while blue curve represents relative permeability of water. It was interpreted from right to left as the saturation of gas increases, the saturation of water decreases. Corey model. Firstly, the pressure, water and saturation from SCA report are tabulated. Next, we find normalized water saturation by using equation 8. It gives us the normalized water saturation for drainage curve. The relative permeability of water is calculated using equation 10, and by using equation 11, the relative permeability of air is calculated. Relative permeability of water and air versus mean water saturation graph was plotted, and the drainage capillary pressure curve was obtained. The blue curve represents the relative permeability of water, while the green curve represents the relative permeability of air. From the table, it is interpreted from right to left. As a result, when the saturation of gas increases, the saturation of water decreases.
In the Brooks-Corey model, we adjusted SWIR to 0.009 to achieve high coefficient of determination R². The normalized water saturation was then calculated using equation 8. Plotting ln PC against ln normalized water saturation gave an R² value of 0.9987, validating the model. The gradient plot, negative 1.524, provide a lambda value of 0.656 as shown in the yellow table. We then calculated the relative permeability of water and air using the Brooks-Corey model formula. The resulting curves resemble those in the Corey model. Note that this model does not represent the SCAL report precisely as the SWIR was adjusted. The relative permeability versus water saturation graph illustrate drainage, read from right to left, with the blue curve representing water, the wetting phase, and the green curve representing air, the non-wetting phase. As the air saturation increases, water saturation decreases.
To conclude, the results show that the precise relative permeability is the best model to represent the wetting phase data only, but thus not suitable for the non-wetting phase data. Both the Corey model and the Brooks-Corey model provided nearly identical results, which is effective for non-wetting phase data, while providing consistent results for drainage curve. On the other hand, it's possible to derive the capillary pressure function from the relative permeability data to offer deeper insights into fluid interaction and helps in predicting fluid behavior.